Hello guys, good evening. What have we done last class? Where were we? Last part? Yes, Aro, just 2 minutes, wait. Okay, so last thing we discussed plus M minus M effect, right? Okay. Okay. So one just quick revision here regarding resonance. Okay, resonating structure that we draw. Okay, resonating structures the are the hypothetical structures. Okay, these structures are the different representation of a molecule or ion. For example, suppose I take a carbonate ion. Carbonate ion is this CO minus, double bond O, and O minus. Okay, this is carbonate ion CO3 2 minus. Now this carbonate ion, you see, here we have the condition of this thing, conjugation is there. We have 3 lone pair on oxygen, 3 lone pair on oxygen, and hence we have one negative charge on it. Okay, so lone pair sigma pi bond, there is conjugation, right? And hence it shows what? It shows resonance. So we can draw the various resonating structure of this by the shifting of pi electrons and lone pair. So when this lone pair converts into pi, this pi converts into lone pair. That is interconverting interconversion of lone pair into pi bond and pi bond into lone pair. The structure that we get here is this. We have oxygen double bond C. This oxygen will be as it is. And here we have one negative charge on this oxygen. Okay. So again, these two oxygen will have 3 lone pair, which is this. Okay. Further, you see, we have resonance possible here, pi sigma lone pairs. This can also come over here, and this goes onto this oxygen. So the structure here, the resonating structure we get is this. C single bond O minus double bond O and single bond O negative. And each of this oxygen has 3 lone pair on it. Like this. So these are the resonating structures. Real structure is not this. All these are hypothetical imaginary structures. The real structure of carbonate ion, which we call it as real hybrid, and that is this. The real structure is this for carbonate ion. We have a partial double bond character from this side to this side, and partial double bond character here also. Okay, and each oxygen atom will have charge on it, and that charge is -2/3. This 2 negative charge equally distributed over the 3 oxygen atom. So this is the real hybrid structure of carbonate ion, and it is the real structure. Actual structure is this. This is just a representation of this real ion. This one, this one, this one. 3 different representations we have. Clear? See, 2/3 charge part, there are 2 possibilities into this. Okay, we can write charge like this, or we can also write delta negative charge on oxygen atom. All these 3 structures are same, so they have equal stability. See, when you draw resonating structure may have equal stability or different stability also possible. Means it is possible that one of the resonating structure is more stable than the other one. Okay, and it is also possible that all RS that you have drawn all have the same stability. So in this case, the stability is same for the 3 molecules, the ion that I have drawn. Okay, hence what we say that this negative charge, -1 -2 negative charge we have total, it is equally distributed on the 3 oxygen atom, right? So 2 negative charge distributed over 3 oxygen atom equally. So 1 oxygen atom will have charge what? -2/3. So you can write this way, or you can also write -2/3 on this oxygen, this oxygen, this oxygen, that is also right. Got it? Understood? Okay. So what have we discussed last class? We have discussed, you can also write delta negative, that is also fine. PM, not wrong. Delta negative on each oxygen atom you can write. Yeah. So last class we have discussed +M -M effect. Okay. And we have seen the condition of the group to show +M or -M effect we have, correct? Okay. And we have also seen that these 2 effects, +M or -M, that affects the ortho and para position, right? Meta position is unaffected by this. which means any group which is present at the meta position, right, does not show resonating effect. Okay, you see, this is the ring we have, benzene ring, and on the benzene ring, this is the group attached on the ring. These two positions are ortho position. We have discussed this. So we have two ortho position, we have one para position, and we have two meta. This one is meta, and this one is also meta. Okay, so the effect of the plus and minus M effect takes, we see the effect at this position, ortho and para position. Meta positions are not affected by this. Okay, now we'll see some examples, and we have to identify here that what effect is there, plus M or minus M, or plus I or minus I. Okay, so all of you write down this. NH2 attached onto this. What effect is there? Tell me, what effect is there in these molecules? Done, all of you? Okay. Now you see, here we have nitrogen and here we have carbon. Do we have electronegativity difference between carbon and nitrogen? Do we have electronegativity difference? Yes. Which one is more electronegative? Nitrogen is more. So obviously nitrogen drags the bond pair of electron towards this side, right? So minus I, it shows, right? It shows minus I. Any doubt in this? No? Guys, respond. Minus I, no doubt. Okay. With minus I, you see, this nitrogen also has a lone pair on it. We know when the first atom has lone pairs, it has electron releasing tendency, right? This electron pair comes over here, this goes over here, right? So with minus I and plus M, it has both effect. Minus I effect it shows and plus M effect it shows. But the property we always check stability and other things with respect to the effect which is a dominating effect. Okay. So one note you write down here, resonance effect, write down, resonance effect dominates inductive effect. Resonance effect dominates inductive effect. Okay. So here, which effect is dominating? Plus M effect dominates, and we say this group shows plus M effect. But it also shows minus M. Plus M is more dominating. So we'll find out the criteria or the property of this with respect to plus M effect. Clear? Again, this oxygen has two lone pair on it. So obviously it shows plus M. Will it show minus I? Minus I possible? Yes, because oxygen is more electronegative. So here also minus I possible, but again plus M dominates minus I. Yes, resonance dominates. Okay. Nitrogen has one lone pair on it. So obviously it shows plus M. Right. And minus I also, but again plus M dominates over minus I. At least one lone pair. At least one lone pair. I have discussed all these things last class, no? On the first atom, the atom which attached with the ring. You are not there in the last class, Oro? Did you revise? That's why these doubts you are getting, no? Anyways, here you see nitrogen has positive charge. There is no lone pair of nitrogen, so it won't show plus M or minus M, but it shows only minus I effect. Only minus I possible here. Okay, this one will show. This one will show. We have a double bond between the first and second atom, so it shows minus M only. Minus I is not possible. Okay. Cl chlorine has three lone pair on it. So it shows plus M and it also shows minus I. Right? Here it shows minus M and this one shows minus M or minus I, but again minus M dominates minus I. Okay. In case of chlorine, it is an exception. Chlorine has plus M and minus I, but its minus I effect dominates plus M effect here. So this is an exception we have. right? Minus I of chlorine plus M of this. Okay, so in case of halogen atom, if halogen atom is attached to the ring directly, then the minus I effect dominates. Write down this exception. Done? This one, this one. Nitrogen does not have lone pair on it, no. It has no lone pair, so it cannot donate. Plus, it cannot withdraw electron also. But minus I will always be there because the bond is there, no. And we know nitrogen is more electronegative, plus positive charge on nitrogen. So its electronegativity is more. It will drag the electron pair towards this side, hence minus I. All of you understood this? If you do not know how these effects are there in the molecule, you cannot do any questions on this. Okay, this is the first thing that you should know. Which group shows plus M minus M plus I minus I, and which one is dominating? Based on this only, you can do questions. Okay. Now, one more concept we are going to discuss here, that is aromaticity. Aromaticity. Aromaticity for JEE, there are many things we have to discuss in aromaticity. But for KVPY, just you require the basic understanding of aromatic compound. Okay. So I am just taking those concepts which is required or which is sufficient for KVPY. JEE thing, I am not doing it now. We'll see this later. Okay. So aromaticity, write down, it is the property of cyclic conjugated planar compound. Means the compound must be a ring, cyclic compound should be there, and it must be conjugated. Conjugation, we have discussed what is conjugation, okay, and what all compounds are conjugated compounds we have. Okay, now based on this, we have three different types here. Okay, the first one is aromatic compound. Aromatic compound. Just you need to know the condition, you have to apply these conditions to get the answer. Aromatic compounds are those compounds which are cyclic, first of all, which are cyclic. The second condition is what? It must be planar. Planar means all the atoms should be sp2 hybridized, okay, and conjugated system. Conjugated system. Molecules must be conjugated. And the fourth property that it follows HUCKLES rule. HUCKLES, HUCKLES rule. Okay, HUCKLES rule is what? According to this, the system should have 4n plus 2 pi electrons. Means the number of pi electrons should be 4n plus 2, where n is any number, 0, 1, 2, 3, 4, and so on. Okay. For example, you see, if I draw this structure, and you need to find out whether this compound is aromatic or not. Okay. Tell me, the molecule is cyclic. Is it cyclic? Yes, the ring structure cyclic. Is it planar? Yes, it is planar because all the atoms are sp2 hybridized. Planar. Okay. Trigonal planar geometry, we have sp2 hybridization means planar. Is it conjugated? Is it conjugated? Yes. What type of conjugation we have in this? Pi sigma pi. Conjugated. Follows Huckle's rule. So Huckle's rule, to find out Huckle's rule, you need to count the number of pi electrons. So how many pi electrons we have in this? The number of pi electrons are 6, because we have 3 pi bond and 1 pi bond has 2 electrons, right? So we have 6 electrons, correct? You know this 6 electron, it follows Huckle's rule for n is equals to what? For n is equals to 1. So for any value of n, if the number of pi electrons follows Huckle's rule and these 3 conditions are satisfied, it means this compound is what? This compound is aromatic compound. Clear? Easy? This is what you need to know. That's it. Clear? Yes, pi electrons means the number of electrons present in pi bond. So one bond will have 2 electrons. 3 bonds, 6 electrons. Got it? Clear? Okay. Next type of compound in this we have. Second one. This is anti-aromatic compound. Anti-aromatic compound. Okay. What is the condition for this, you see? Just you need to know the condition and check for the given molecule. First condition is cyclic. Second condition is planar. Third condition is system must be conjugated. Conjugated system. Fourth one, which differs from the aromatic compound, is it has 4n pi electron. 4n pi electrons. In the previous one, we have 4n plus 2. It is 4n pi electrons, where n is again any number 0, 1, 2, so on. For example, suppose you have a compound this. Tell me. First of all the carbon atoms are sp2 hybridized, so it is planar. Cyclic. Pi sigma pi conjugated system it is. And number of pi electrons, if you count, that is 4. Yes or no? Number of pi electrons 4. So it follows this 4n pi electron for n is equals to 1. Hence this compound is what? This compound is anti-aromatic compound. AA. Anti-aromatic. Any doubt? It's just the name of the compound, Shitish. Okay. We'll discuss one more property of this, but aromatic, anti-aromatic are the names. That is it, nothing much. Why didn't you ask me why it is aromatic? Okay, so for name we cannot say anything. Okay, that's the name. But yes, the property of these two compounds, the first one and this one, if you see, it is exactly opposite. We'll see that. We'll see that. But before that, we'll see one more type of compound we have, and that is non-aromatic compound. Non-aromatic compound. Non-aromatic compounds are those compounds which are not cyclic. Okay, open chain compounds are non-aromatic. No, it's not like that. This aromatic has nothing to do with the aroma or the term that we use for the smell and all, right? It has nothing to do with that word. It is not cyclic. Okay. If it is cyclic, but not conjugated, that is the condition. If it is cyclic, but not conjugated. Okay. Right. These compounds are what? These compounds are normal compounds. This is not the condition actually. These are normal compounds that we have. Normal compounds. In terms of stability, we are talking about. Stability is not great, not that high and not that low. Okay. Example, you see. This compound, non-aromatic compound. Open chain, whenever you see it is non-aromatic, without any other thought. Non-aromatic. This one, non-aromatic or what? What about this one? Last one, you tell me. Last one is also non-aromatic because you see this carbon atom is sp3 hybridized, correct? This carbon atom is sp3 hybridized, hence the conjugation is not there in the entire ring. Conjugation should be there in the entire ring. Then only it can be aromatic or anti-aromatic. But if you see any sp3 hybridized atom in the ring, it is non-aromatic. That's it. That is it. Simple. Any sp3 hybridized atom in the ring, non-aromatic. That is it. Clear? Yes, we have here, but this side the conjugation is not there. What I said, conjugation should be there in the entire ring, not the half part of the ring. Like for example, if I draw this one also, you see, this compound, here and here. Here we have conjugation, but this side we do not have conjugation, correct? So this one is also non-aromatic compound. Got it? Ansh. Okay. Now, the another thing which is important, and they have asked this question many times, the stability order of these compounds, stability order, aromatic compounds are the most stable compound. Aromatic compounds are highly stable. Okay, they have extra stability. After this, we have non-aromatic compounds. The stability of non-aromatic compounds is more. And then in the last, we have anti-aromatic compounds. Okay, so this order you must remember. Okay, it's very, very important. Okay, they may give you some compounds and they'll ask you about the stability order. Maybe you can easily find out which one is anti-aromatic, aromatic, or non-aromatic, and accordingly you can write down the stability order. Correct. Aromatic compounds has, we say, they have some extra stability, right? Its stability increases, extra stability, because of the delocalization of electron. Electron delocalization decreases overall energy because of the uniform distribution of electron. The energy decreases and hence stability increases. Anti-aromatic compounds, right? This has least stable. These are the least stable compound, right? Energy is higher over here. This is the normal compounds, like I said. Stability falls in between these two. So stability order is this, but the energy, if you see, the order of energy for these compounds, it is not like more stability means more energy. It is not like that. In chemistry, always lesser energy state is more stable state. Always keep that in mind. Okay. Less energy, more stable. So the energy order is this. Energy increases from left to right. Clear? Okay. Let us discuss some example on this. You have to write down which one is aromatic, anti-aromatic, and non-aromatic. Negative charge. This is positive charge. This is negative. This is negative. Positive. Positive. Some more examples I'll write down. Try all of you. Okay. Wait, we'll discuss one by one. See, the first one I have discussed already. So this is aromatic. This one is anti-aromatic. This one is non-aromatic. sp3, sp3. Here also the carbon is sp3. So it is non-aromatic. Carbon has one lone pair. The system is conjugated, correct? Pi sigma lone pair. The system is conjugated. Ring system already we have. And number of pi electrons you see, this lone pair we also count into the pi electrons. Okay. So one pair of electron here, one pair here. 4 pair of electron, it is anti-aromatic. This has positive charge. The system is conjugated, but here we do not have any lone pair, but one positive charge. So only 2 pi electrons, it is aromatic compound. Tell me, any doubt in these three? Tell me any doubt. Okay. See here, second one, this one, right? See, you don't have to think about these methyl group, which is present here. Aromatic behavior is because of the ring, correct? So if ring is present, we'll consider ring only. Just you ignore this and this. We have a ring, cyclic planar conjugated, has 4 pi electrons. The number of pi electrons also, if I write down here, the number of pi electrons, here we have 6 pi electron. Here we have 4 pi electron, right? Here we don't have to count the number of pi electron because it is non-aromatic already, right? This one is non-aromatic because it is sp3 hybridized. This one has 4 pi electron, conjugated system. Positive charge, it has 2 pi electron, aromatic. This one, right? This one. So this one is this ring now. You see, it is a 3-membered ring. So it is cyclic. First condition is fine. 1 pi bond and 1 positive charge. So you see, this carbon is sp2 hybridized, so planar. And pi sigma positive charge, it is conjugated also. Number of pi electrons, if you count, we have only 2 pi electron here. There is no electron pair here. So we have 2 pi electrons. It follows HUCKLES rule for n is equals to 0. Hence it is aromatic. Did you get it? Any doubt in this? Which one? This carbon. You see, we have 1, 2, and 1 hydrogen present here. No? So 3 sigma bond, sp2. Correct? So this one, you see, it is a conjugated system, pi sigma lone pair, and then pi sigma lone pair. The entire system is a conjugated system, correct? Number of pi electron is 2, 4, 6. So it has 6 pi electron. So this one is also aromatic in nature. Okay, this one is conjugated, right? But only 2 pi electrons. It is also aromatic in nature because this positive charge we don't consider. Carbon atom here is sp3 hybridized, so it is non-aromatic. This carbon atom sp3 hybridized, non-planar, non-aromatic. Positive charge system, now it is conjugated, sp2 hybridized carbon, 2 plus 2, 4 electron. 4 electron means it is anti-aromatic. 2 plus 2 plus 2, 6 pi electron, it is aromatic. It is 4 pi electron. Tell me. Did you understand, all of you? Yeah, we'll discuss some more. Did you understand all this? So always remember one thing, in a ring, if one atom has 2 lone pair, then for aromaticity, we count only 1 out of 2. We won't count the 2 lone pair present on one atom. Here you see lone pair we are counting. For example, I'll show you some example here. What about this one? These 4 compounds, you tell me. Okay. Now you see this compound, you see oxygen is present in the ring and oxygen has 2 lone pair, right? So for aromaticity, out of 2, we count only 1 lone pair of electron. To get the number of pi electron, both lone pair we won't count. We have reason for this, okay? But that I am not discussing now, okay? That you let it be, that things will get complex then, okay? For solving questions, you just have to keep this in mind. Whenever one atom has 2 lone pair, out of 2, we count only 1 to get the number of pi electrons present. Here also we have 1 lone pair. One more thing, they won't give you this lone pair like this, they won't give you. You should know this, that when oxygen attached with 2 bond, it will have 2 lone pair. Nitrogen with 3 bond, 1 lone pair. You should know this. Now, this carbon atom you see, it is sp3 hybridized. So it is non-aromatic. Here it is conjugation, right? Lone pair, sigma, pi, sigma, positive charge, sigma, it is in conjugation. So number of pi electrons, if you count, it is 2 plus 2, 4 plus 2, 6 pi electron, and it is aromatic in nature. Okay. This one, if you see, 2, 4, 6, 8, 8 pi electron, it is anti-aromatic in nature. This one has 2, 4, 6, 6 pi electron, it is aromatic in nature. Right? This compound, we call it as pyrrole. Right? There's one more compound, you should know this. Which is this 1 lone pair on nitrogen, and this is the bond, pi bond we have. Now in this, this lone pair is not involved in resonance. Okay, the name of this compound is pyridine. Right, this lone pair in pyridine is not involved in resonance. 2, 4, 6. It has 6 pi electron and it is aromatic in nature. Understood? One point to write down: if nitrogen is sp2 hybridized, just a second. If the nitrogen is sp2, yeah, sp2 hybridized, if the nitrogen atom is, just a second, Pradyun, sp2 hybridized, then the lone pair present on the nitrogen atom if the lone pair present on the nitrogen atom is not involved in resonance. Okay, nitrogen atom sp2 hybridized, not involved in resonance if the lone pair present on that. Right, this is what you need to keep in mind. If nitrogen is not sp2 hybridized, if it is sp3, like in this case, you see, it is involved in resonance, and we count that. Correct. Now, based on this, one more question they ask. You see here, if I talk about the basicity of these two compounds, basicity is what? Tendency to lose lone pair of electron. Correct? So this lone pair and this lone pair we have here. But this lone pair is actually, it is involved in resonance. It is not present on the nitrogen atom. It is delocalized, correct? It is moving on this molecule like this. It is not static, not present. Hence, it is not present, right? Hence, this lone pair is not present on nitrogen, and its donating tendency will also be less. Correct. So hence the basicity, if you compare, pyridine is more basic than pyrrole. Got it? Tell me. Reason for this, why this lone pair is involved and why not involved, that also we can discuss by looking at the orbital there. But eventually you have to keep this in mind only. That's why I have given one simple line for this. That is, if nitrogen atom is sp2 hybridized, you don't count this lone pair. if it is sp3, you have to keep this in mind, right? We'll count that. Some more examples we'll see in this. This compound, this compound, for these two, you tell me. The first one you see, this nitrogen atom has 1 lone pair, but obviously this lone pair we won't count because all the nitrogen atoms are sp2 hybridized, correct? So it is 2,4,6 pi electron, and this is aromatic in nature. This one also, system is conjugated, 2,4,6 pi electron, it is aromatic. Any doubt in this? Okay, so there are many other, kind of compounds which, which is there in aromatic compounds. But yes, at this level, you won't be getting all those things. Okay, you will get confused. For KVPY, this much is enough. This is the basics of aromaticity that you should know. That how do we decide a given compound is aromatic or not? Okay. We have discussed also plus M minus M, all those effects. Okay. The stability of various intermediates, write down. The stability of various intermediates are also affected by resonance. Are also affected by resonance. For example, you see, if you see the stability of carbocation, right? Carbocation, it is directly proportional to, in the previous one we have discussed plus I, right? So here also it is directly proportional to the electron releasing effect, which is plus R, and electron withdrawing effect inversely proportional minus R. Okay. Write down that stability of intermediates is also affected by resonance. Is also affected by resonance. And then you write down this. Okay. So two things we have discussed, inductive effect and resonance. Okay. And both affects the stability of intermediates. I have just given you an example of carbocation. Similarly, we have for carbanion also. Stability of carbanion would be what? It's directly proportional to minus R and inversely proportional to plus R. We'll see examples on this. Okay, just write down this. Done? Can I move on? Tell me. Okay. Next, write down the third type of electronic effect we are going to see now. And that is hyperconjugation. Okay. Write down. Hyperconjugation. Write down, this is also known as it is also known as sigma pi resonance, like this. Sigma pi resonance or no bond resonance. It is also known as sigma pi resonance or no bond resonance. Okay, what is hyperconjugation that we'll see? And this is applicable, write down, applicable only with alkene, carbocation, and free radical. One note you write down after this. One note you write down. Okay, one note you write down. It is not applicable for carbanion. It is not applicable for carbanion. Done. Now you see what is hyperconjugation and what happens in this. I'm taking an example of alkene. So this example you see carbon with 3 hydrogen, CH double bond CH2. Okay. So what happens in this? This bond pair, which is present here at the adjacent carbon of the double bonded carbon. Double bonded carbon is this too. Adjacent carbon is this. So this carbon, we also call it as alpha carbon. Okay, this is alpha carbon. So from alpha carbon, what happens? This sigma electron, it comes over here, and this pi electron jumps onto this carbon. So what happens because of this, you see? We get H here. See, this H will be as it is. Here we'll have this H plus. Because the pair of electrons shifts over here, so it's H plus, double bond CH, single bond CH2, and negative charge on this, because it takes pi electron from this. Okay, so this sigma converts into pi, correct? That's why it is sigma pi resonance, first of all. Okay, no bond resonance, why? Because the H plus is present over here. It is not going out of this molecule, means it won't leave this carbon atom completely. Okay, it will be present here. Hence, it is no bond resonance. Okay, so we can draw this structure, or it is also possible that this sigma comes over here and we get this structure. So another structure is this, which is possible. H plus here, carbon with hydrogen, double bond CH, single bond CH2, negative on it. This is also possible. One more structure possible here, which is this. H, C, H, H plus, double bond CH, single bond CH2, and negative charge on it. These three structures we can draw in this molecule. Right. These H plus here, it is present over there without any bond. Hence, we call it as no bond resonance. Okay. So, if they ask you the number of hyperconjugative structure, we always count the structure that we can draw plus the given one. Okay. You see, this is alpha carbon and hydrogen attached with this alpha carbon, we call it as alpha hydrogen. So the number of alpha hydrogen we have, right, equal number of structure we can draw apart from the given one. Okay, so the question, if they ask number of hyperconjugative structure, that would be the number of alpha hydrogen, because equal number of structure we can draw, plus the given structure, which is 1. So number of alpha hydrogen plus 1 is the number of hyperconjugative structure. Condition is also this. We must have alpha hydrogen present. Write down the condition for resonance.
Got it? Right. Similarly, we can also have hyperconjugation in carbocation and free radical. Okay. So this is what this hydrogen is. Here you see, right? Number of hyperconjugation, alpha hydrogen is what? The hydrogen which is attached with the alpha carbon. So this is double bonded carbon atom. So this carbon atom bonded with a double bond. Adjacent to this carbon atom, the carbon atom we have, we call it as alpha carbon. So you see this carbon is the alpha carbon and hydrogen attached to this alpha carbon is alpha hydrogen. And number of alpha hydrogen we have, equal number of hyperconjugative structure we can draw like this. But if they ask you the number of hyperconjugative structure, your answer will be the number of structure that you can draw plus the given one. This also we count. Hence, number of alpha hydrogen plus 1. Got it? Right. So just you need to check, is there any alpha hydrogen present or not? If alpha hydrogen is not present, hyperconjugation is not possible. Okay. For example, you see, calculate the alpha hydrogen in these structures, if it is there. The number of alpha hydrogen. This one. This one. Just you find alpha carbon and the number of hydrogen attached with the alpha carbon is the alpha hydrogen. These compounds. Finish all. Done? Okay. So first of all, what I said, you need to just locate the alpha carbon. Correct. You see, this is alpha carbon. 1, 2, 3, and 4 alpha carbon we have. And each alpha carbon has 3 hydrogen. So number of alpha hydrogen we have here is 12. This carbon, you see, we have 2 hydrogen present, 2 alpha carbon we have. So number of alpha hydrogen is 3 plus 3, 6. Here the number of alpha hydrogen is 2 carbon again. Each carbon atom has 2. So number of alpha hydrogen 4 here. I'm sorry, it is 4. Number of alpha hydrogen, could you tell me here? 1, 2, 3, and 4. So 4 into 2, 8. Here, for this double bond, this is the alpha carbon and this is the alpha carbon. So 2 plus 1, 3. For this double bond, this is the alpha carbon. 2 plus 1, 3, 3 plus 3, 6. Number of alpha hydrogen here, alpha carbon, alpha carbon, alpha carbon, alpha carbon. 3 plus 3, 6 plus 4, 10. Number of alpha hydrogen here, 1, 2, 3, 4 carbon. So 1, 2, 4, 6 alpha hydrogen we have in this. Tell me, any doubt in this? Clear, guys? Alpha carbon, Aditya, is the carbon atom which is adjacent to the double bond. Means you see in all these molecules, the double bonded carbon atom is this. So adjacent to this double bond is what? This carbon and this carbon. These two are alpha carbon. This double bond, 1, 2, 3, 4 alpha carbon and so on. Did you get it? Yes, number of hyperconjugative structure is the number of alpha hydrogen plus 1. If they ask you the number of hyperconjugative structure, we need alpha hydrogen for hyperconjugation. That is also sp3 hybridized. Means the adjacent carbon, the alpha carbon must be sp3 hybridized. Okay, then it happens. Okay, now one more thing, the stability of alkene is affected by hyperconjugation. Means suppose if I ask you this question, just one question we'll see, we won't go into that detail because it is affected by this, so you can understand it easily. Okay, suppose I'll write down this one first. The stability of alkene is directly proportional to the number of alpha hydrogen atom. Okay, for example, if I ask you the stability order for this molecule, this molecule, this molecule, this molecule, and this molecule. These 4 compounds, the stability of alkene you have to compare. Okay, so more number of alpha hydrogen means more hyperconjugative structure we can draw, and hence the stability will be more. So calculate the alpha hydrogen for each molecule and find out the order. Okay, so obviously the number of alpha hydrogen in the first one, if you count, it is 12, and here it is 9, here it is 6, and then it is 3, right? The reason for the stability is what? That more alpha hydrogen, then more hyperconjugative structure you can draw, more uniform distribution of charge, more shifting of electron, right? And hence the stability will be more. So stability order is this for alkene. Clear? No doubt? Just you need to keep these rules in mind, that is it. Okay. For example, stability you compare in this one and this one. Alkyne also hyperconjugation is possible. Stability order. Done? Okay. The first one, again we count alpha hydrogen. Number of alpha is here, could you tell me? Number of alpha hydrogen. This is the alpha carbon, this is the alpha carbon, and this is the alpha carbon. So 3 plus 2 plus 2, 7. Here the number of alpha hydrogen, we have only one alpha carbon here, which is this. So only one hydrogen, hence first one is more stable than the second one. In this one, both of this carbon atom, this one and this one, are the alpha carbon. So it is 6, and here it is 5. First one is more stable than second. We'll discuss resonance. We are just talking about here hyperconjugation. Obviously, in this ring, we have a resonance possible, but we are talking about hyperconjugation. So hyperconjugation, like I said, it is possible in alkene. I forgot to write here. In alkyne also it is possible. Alkene, alkyne, it is possible. It is possible with carbocation and free radical. Okay. Now this molecule that I have given here, this molecule shows it is giving electron, this part is giving electron to this molecule, right? So this kind of effect, we call it as plus H effect, plus hyperconjugation. Okay, plus H effect. Right. I'll just write down this just a second. So this we have done. Hyperconjugation, like I effect and resonance. Hyperconjugation, we also have two types. One is plus H effect and other one is minus H effect. Plus H and minus H. Plus H, the example we have already done, that is CH3CH double bond CH2. Okay. For example, you see this, the same example I am taking. CH double bond CH2, hydrogen, hydrogen, and hydrogen. So this here, what happens is, I'll draw only one structure here. This comes over here and this pi electron jumps onto this carbon. So we get what? HCH plus, H double bond C, H single bond CH2, negative charge on this. So this is releasing electron plus H effect. Okay. Now minus H effect is what? Only one atom we have which shows minus H effect, and that is chlorine. Right. It takes the electron from the molecule. For example, you see this. Suppose we have Cl, carbon, Cl, CH double bond CH2. Now in this, what happens? This pi electron comes over here and this is taken up by this chlorine, because chlorine is more electronegative. Okay. So the structure that we get here is exactly same like we have drawn up, but here the chlorine will have the negative charge. This chlorine will be as it is, double bond CH, single bond CH2, positive charge on it. This is minus H effect, only possible with chlorine. It is not very common, okay, but you should have this idea. Okay, you won't get this minus H effect in KVPY kind of thing. Right, but you should know this. So only one molecule we have, chlorine, which shows minus H effect. Write down. Done? No, fluorine is more electronegative, but at the same time, its size is small. So bond length is small there. And hence it is difficult to break this bond. Hence fluorine does not show. Okay, so minus H effect, we have only one atom, that is chlorine, not any other. Now you see. So all these, here also you see, if I talk about the application of hyperconjugation, in just a second. Application of hyperconjugation. So suppose you're talking about the stability of carbocation. Stability of carbocation. It is again directly proportional to plus H and inversely proportional to minus H. Stability of carbon ion. Stability of carbon ion. Directly proportional to minus H, inversely proportional to plus H. Okay. So now all these three effects we have discussed, right? And one thing is common in all these electronic effects, that it affects the stability of carbocation intermediates. Even it affects the acidic behavior also, the same way that we did in I effect. Now, when you get the question in the exam, first of all, you have to identify that which effect is present. It is possible that in a given molecule, you have inductive effect, you have resonance, you have hyperconjugation. All three cases possible in one molecule, right? So first of all, you have to identify, okay? And once you identify, then you should know the preference order of this effect, means which order we should, which electronic effects we should give the preference to determine the stability and other things, right? So the preference order we have, it is R, H, I. Resonance dominates all other effect. Resonance, hyperconjugation, and inductive effect. Got it? Correct. Now, this is very important because you're not going to get the question from only I effect or resonance or hyperconjugation. You have the basic idea of these three effects. Now you should find out that in which molecule, the given molecule, which effect is there, and accordingly we'll see the order, okay, of other things. Like for example, you see this question and tell me the stability of this double bond. Which alkene double bond is more stable? This one or this one? Which one is more stable? This two? Which alkene is more stable? Okay, yes, Ans, correct. Tell me the answer, guys. I'm waiting. I got only one response. See here what happens. The oxygen has lone pair on it. So this pi bond is involved in resonance. So basically we can say here we have resonance possible, but here we have hyperconjugation. Right, the alkene is getting stabilized through hyperconjugation. We know resonance dominates hyperconjugation. Hence, the answer would be this stability order. Same thing here you see, we have pi sigma pi conjugation. This is resonance. And here we have hyperconjugation again. Correct? This is more stable because of resonance. Order is this. Done? Could you tell me which carbocation is more stable here? And the reason for stability. CS3C, CS3, positive charge, and CS3CH, CS3, positive charge on this. Which one is more stable? Okay. A is more stable than B. And what is the reason for the stability of A? More plus sign. Okay. Your order is correct. Okay. Your order is correct, but the reason is not right. Because you have set this plus I because we have done the same thing in I effect. But since now we have done all the three electronic effects, then in a given molecule, you have to consider that what all effects possible, first of all. First thing is what? You need to find out the effect, possible effect, right? So what all effects are there in this molecule? Could you tell me? Do we have resonance? No. Do we have I effect? Do we have I effect? Yes. So we have plus I effect. Do we have hyperconjugation? Hyperconjugation. We have alpha hydrogen. No, you see. Carbocation, alpha hydrogen we have here. You see this? See this. Alkene, alkyne, carbocation, free radical. Okay. So that is what you need to keep this in mind, that where it is hyperconjugation is possible. Correct, guys? So all of you agree with me? Do you have that we have here hyperconjugation possible in this molecule? Wait just a second, Kshitish. Plus I and plus H possible here. But which one is dominating? Which one is dominating? H. So this is the order we have, and hence we'll count what? We'll count alpha hydrogen here. Okay. So you see this molecule, this one has how many alpha hydrogen in the first one? How many alpha hydrogen? 3 plus 3 plus 3, that is 9. Alpha hydrogen here, that is 6. Okay. So the one which has more alpha hydrogen is more stable. Order of stability is this. Got it? You can use I effect also here. You'll get the same answer. but sometimes you won't get same answer with I effect. I'll give you one example. You see this one. We have CH3, CH3, positive charge on it, and we have CH3, CH positive charge, CH2, CH3. Tell me, which one is more stable? Why A greater than B? Right. So obviously we'll use hyperconjugation. So the number of alpha hydrogen here it is 6. Number of alpha hydrogen here it is 5. Right. If you think of I effect here, so here we have plus I of methyl, plus I of methyl, here we have plus I of ethyl. So plus I of ethyl is more than to that of methyl. We know larger group can release more electron. Okay, larger group releases more electron, correct? So if you consider the I effect here, this has more tendency to release electron, and hence this will stabilize the carbocation more than this methyl. Hence, due to I effect, the order of stability is this, due to I effect. But the actual order is what? Actual order is opposite of it, which is this. Why? Why? Because we have hyperconjugation possible here, and hyperconjugation is the dominating effect. Hence, we'll find out with hyperconjugation. Okay, not with I effect. So what we need to do? We need to just find out first what effect is there, and depending upon the preference order, that is R, H and I, will compare the stability. Suppose in a given molecule resonance possible and hyperconjugation also possible. So first we'll try to compare with resonance. If we can do it, fine. Otherwise we'll go for hyperconjugation, and then we'll go for I effect. Did you get it? No, conjugate system, we don't have, we just check resonance there, that is it. In conjugate system, we'll see how many RS are there. Suppose the two molecule shows resonance, I'll show you that example also. Suppose the two molecule shows resonance, then the one which has more resonating structure is more stable. Right, in case of resonance, we'll do like that. More resonating structure means what? More like delocalization of electron, more uniform distribution of electron, and hence more stability. It is not same. It is pi sigma pi and pi sigma lone pair is different, but both shows resonance. So if one of the molecule has pi sigma pi, another one has pi sigma lone pair, right? Then if they have same number of resonating structure, then their stability will be same. But we consider resonance in both cases. The one which gives more resonating structure is more stable. We don't see whether it is pi sigma pi type of conjugation or pi sigma lone pair type of conjugation. Got it? Okay. Another one very important thing, don't check I effect. Okay, I effect won't help you much. Okay, you should know the concept, but always think of resonance first if conjugation is there, then you think of hyperconjugation. If you are not getting it by hyperconjugation, suppose we have same alpha hydrogen present in the two molecule, then we'll think of the other effects, which is the I effect. Okay, see this one. Order of stability of carbocation. A, B, and C. Reason also, you tell me what effect you are taking. Done. Okay. Could you? Yeah. Okay. Number of, first of all, what effect possible here, here, and here? Do we have I effect possible? We have plus I and we have plus H, no resonance, correct? But we'll compare plus H. How many alpha hydrogen we have here? 3 plus 2 plus 2, 7. Number of alpha hydrogen here, 1 plus 2, 3. Number of alpha hydrogen here, that is 1. Only 1 over here, right? Hence, the order of stability is this. What effect we have here? Plus H. What effect we have here? Plus R. Resonance, basically. Okay. So this is more stable than this because we have H and R here. Order of stability is this. What about here? What about this? Here we have resonance. And here we have hyperconjugation, correct? Plus H. With 2 alpha hydrogen. Not required to count this. Order of stability is this. Okay. This one you compare. CH3, CH2, CH2 positive charge, CH3 CH2, CH2 CH2 positive charge. Compare this one. No, here better we say resonance. Okay, don't say plus R or minus R because it is present in the same molecule. So better you say this positive charge is getting stabilized through resonance. This goes away. In the last one, plus R is electron releasing, minus R is electron withdrawing. Check your notes last class, you will get it. Ansh. Okay, what is the answer in the last one and what is the reason? Right, you see here again, both of the molecules shows hyperconjugation and plus I effect, correct? Number of alpha hydrogen, if you count here, it is 2. And number of alpha hydrogen, it is again 2. Since we have equal number of alpha hydrogen, so we cannot find out the order with respect to hyperconjugation. Correct? Then we'll see what the next electronic effects which is possible in this molecule. And that is nothing but I effect. So I effect of this group is more than to this because of its size, and hence the stability is more for this one. Are you getting it now? Correct? Okay. Always keep this in mind that you have to find out the effect first. Okay? All the effects. Now you see on the ring, if hyperconjugation is there, then how do we do this? Suppose we have a benzene ring and CH3 attached to this ring like this. So obviously we have 3 alpha hydrogen, hyperconjugative structure we can draw. This comes over here and this comes over here. With H plus, H and H. Negative charge. And then we can further draw this structure, a resonating structure like this. So this molecule is this. H plus, H and H. Further, if you draw, this comes over here, this goes here. And further, we can draw the next structure. So what we can say, it is plus H effect. So write down due to plus H effect, plus H effect, the electron density at ortho and para position increases, like we have in plus R effect. Okay, this is the one example we have discussed. Another example, you see, if you have chlorine attached on the carbon, that is minus H effect. So minus H effect is this, suppose. Here we have CCl3 attached. Double bond, double bond, double bond. This shows minus H effect. We have already discussed it. This comes over here and this goes on to this chlorine. So the structure that we draw here is this. Negative Cl, Cl, and here we have the positive charge. Then you draw the resonating structure. You will see the next structure, this positive charge will come over here and then it comes over here. So what we can say, due to minus H effect, right down here, due to minus H effect, electron density decreases at ortho-para position. Copy down this. Done. Done. Okay, one last note in this, you write down that hyperconjugation does not affect the meta position. Does not affect the meta position. It means what? That any group attached at meta position does not show hyperconjugation. Okay. Any group attached at meta position does not show hyperconjugation. Okay. Now, again you write down the stability of carbocation. Now we are looking all the effects into this, whatever we have discussed so far. So stability of carbocation is, you have to follow this order, right? If the carbocation involved in aromatic behavior of the compound, involved in aromaticity, it is most stable. Then the second factor we have plus M effect, right? Third factor we have which stabilize the carbocation, which is plus H effect. Then we have plus I effect. All these effects stabilize the carbocation. Okay. After this we have minus I, minus H, minus M, minus M, and next, the last one is anti-aromaticity. Okay, this is the order of stability we have. This is what we have discussed. Okay, when carbocation is a part of aromatic, it is the most stable one, right? First 4 effects that we have, this is the stabilizing factor. This stabilizes carbocation. Stabilizing factor. This is destabilizing factor. Destabilize the carbocation. Are you getting it, guys? Correct? Now, you see this example here. Compare the stability of carbocation. Here we have NR2, CH2 plus, NR2 and CH2. Which one is more stable in this two? Stability of carbocation. Okay, now you see in this question what we'll do, we'll first of all we'll find out the effects. What effect is there, right? So effect here we have NR2, it has plus M effect. This shows plus M, right? In this two carbocation, the only difference is what? The stability, the position of NR2. It is at para and meta, right? And this difference in position only affects the stability of carbocation. Now at para position, we have plus M, but at meta position, we know plus M plus H not possible if it is, if condition is there also. This position is unaffected in resonance and hyperconjugation. The only effect which is possible here at meta position is I effect, correct? So what effect this group shows? It shows minus I because nitrogen is more electronegative than this carbon. Tell me, any doubt in this? No doubt, right? Which one is stabilizing factor? Obviously, plus M dominates I effect, correct? So the first one is more stable than the second. No doubt. Second question. See this one. Here we have NH2. Then here we have OH. Tell me the order in this one. Okay. Now in this one, you see, first of all, you tell me what effect this group shows. What effect this group shows? Plus M. So first of all, we'll assign the effect. Here also it is plus M. This one, this M, this is minus I. It is not minus H. Minus H possible when we have this. CCl, Cl and Cl, right? Then minus I possible, minus H possible. It is not, chlorine is directly attached to this. So only minus I possible here. Correct, no? Right? Okay. So obviously the third one, this is the destabilizing factor. So this is the least stable. Right? This is the least stable. Now in this two, both shows plus M. So the one which has more tendency to release electron stabilize the carbocation most. Correct? So nitrogen has one lone pair, oxygen has two lone pair, and nitrogen is less electronegative than oxygen, and hence its electron releasing tendency is more than to that of OH. Hence the stability order is this. Correct? Any doubt in this? See this one. This three. Done. Tell me the answer. Yes, guys. See what happens in this. At this position, what effect we have? At this position, minus I. Okay, minus I. Here, plus M, and minus I also possible, but plus M dominates minus I. Correct? Here also we have plus M and minus I, plus M dominates minus I. Even in this case also it is possible, plus M minus I, plus M minus I, plus M minus I and minus I, right? We can write that. Why I have written here plus M and minus I, I'll let you understand this. Wait. So first of all, minus I will destabilize this carbocation. So this one will be the least stable. Okay. Now in this too, you see both shows plus M effect, right? Hence we cannot find out the stability of these two carbocation with respect to plus M. Correct? Both shows plus M. So with plus M we cannot find out. Then we'll see the next effect which is possible. The next effect is minus I, and we know minus I is distance dependent. Effect of minus I is more, over here at this position, since it is closer to this. Here the effect is less. So minus I destabilizes carbocation more than the minus I over here. Hence what happens? The second one is the most stable one, right? And then we have the third one, and in the last we have the first one. This is the order of stability. Is it clear? Is it clear? Any doubt in this? Yeah. Did you understand this? We'll take a break now. All of you understood this? Any doubt in this? No. Correct. So just you assign the effect and then we'll find out the order one after that. Fine, guys. We are going to take a break now. Okay, we'll start at 6:40. Take a break. Hello. Hello, you there? Yeah. Next, you see the stability of this. CH2 positive, and here we have CH3. CH2 positive, CH3. CH2 positive, CH2, CH3. Compare the stability. Tell me, order in this two. Okay. The second one. See, distance factor is applicable only in I effect. Okay, only in I effect distance factor is applicable. The first one, here you see, we have plus H effect at this position. At this position, we have plus I, and here we have again plus H. Okay, the number of alpha hydrogen here is 2, and the number of alpha hydrogen here is 3. So obviously plus H stabilizes the carbocation, right? So stability order is, this is 1, this is 2, and this is 3. Is it clear? Okay, now here you see we have plus H effect possible, and the number of alpha hydrogen is 1. But here we have I effect possible, plus I. Plus H is not possible because there is no alpha hydrogen present here. Alpha hydrogen 0. So no alpha hydrogen, no hyperconjugation. And hence this one is more stable than the second one. Is it clear? Any doubt? Try this one. CS2 positive. Here we have CS3. Wait, I'll check the first question. Let me write down this. CCl3. In the first one, we have alpha hydrogen. No, here it is at this position, meta position, hyperconjugation is not possible. Hence plus I we have here. Got it? Because the position is meta. Okay, Aditya. At meta position, this position, hyperconjugation is not possible. We have seen hyperconjugation affects this one and this position. So any group which is attached at this meta position, acha, this one, in here we do not have any alpha hydrogen. This is carbon, this is carbon, this is carbon. This is the alpha carbon, right? This carbon is the alpha carbon, right? Which does not have any hydrogen. Hence, it is not possible. Tell me the answer for this one. Answer for this one. Here we have plus H effect. And here we have minus H. Here we have minus I. Is it right? Correct. So plus H dominates, like minus I and minus H and minus I, both are destabilizing factor. So this is 1, minus H destabilize more. This is 2, and this is 3. Got it? See this compound? See, alpha carbon is the carbon which is adjacent to the double bond or carbocation. Suppose we have this. CH2 positive charge. Okay, so this carbon is the alpha carbon, this carbon, adjacent to this. Suppose we have a double bond here like this. So this carbon is the alpha carbon. This carbon is the alpha carbon. If you have a molecule like this, suppose, this carbon is the alpha carbon. This carbon is the alpha carbon. This carbon is the alpha carbon, adjacent to the double bond. Got it? Okay. Now you see this question. Done? Okay. Now you look at this question. Done? So in the first one, you see here we have minus M effect. This is plus H, minus H. Minus M, minus H, both are destabilizing factor. Minus M dominates minus H. This means what? This will destabilize more. 1, 2, 3. CHO is what? Double bond here, so it will drag the electron towards the side. Tell me the order of stability. A, B, C, D. Done. What is the answer? Okay. Now you see this. In the first one, this carbocation is resonance stabilized with this. Here also we have resonance, but yes, the resonance here we have with 2 ring, and here we have only 1 ring, right? So we can say in this compound we have more RS resonating structure than this one. Okay, these 2 compounds, if you see, these 2 compounds are aromatic compound. This has 2 pi electron and 2, 4, 6. Here we have 6 pi electron. Here we have 2 pi electron. So both are aromatic. And this positive charge is involved in aromaticity. So we can say the aromatic behavior of this compound we have because of this positive charge. So we say what? This positive charge and this positive charge is resonance stabilized. Oh, sorry, stabilized through aromaticity. Right? Stabilized through aromaticity. So these 2 are resonance stabilized. These 2 are stabilized through aromaticity. But since here we have larger ring, more uniform distribution of electron we have, more number of resonating structure we can draw, right? 6 pi electron. So this compound is more stable than this. This compound is more stable than this. So stability order, if I write down, D is the most stable, then we have C because of aromaticity. And then resonance, if you compare, B has more number of resonating structure, and then A. This is the order of. Did you get it? No doubt in this, correct? Just a second. See, in this question, what happens? These 2 compounds are resonance stabilized. And this, you see the positive charge here, because of this, the compound becomes aromatic. So these 2 are aromatic, these 2 are resonance stabilized. So when same factor we have here, then we'll see the one which has more RS, more resonating structure, is more stable. So B is more stable than A because we have 2 ring here, only 1 ring present here. Here we have large ring, more number of RS you can draw, more distribution of electron we'll have over here. Hence this compound, both are aromatic, but this one is more stable than this because of large structure. Okay, hence D and C both are aromatic compounds. Obviously these 2 are more stable than these 2, and in between these 2, D is more than C. So we have D, C, then B, and then A. Okay, now this question, you see, Tell me the stability order. Done. Okay. So in this, what factor we have? In this, what factor we have? This carbocation is in resonance with this pi bond, correct? Right, this carbocation is in resonance with this pi bond, correct? So here we have resonance. Here also we have resonance. And here what we have? Here what we have? I effect or what? Hyperconjugation plus H. I effect is also there, but hyperconjugation is dominating. So we know resonance dominates hyperconjugation. Okay. So obviously the third one is the least stable, that is 3, because hyperconjugation. Now both has resonance. The one which has more resonating structure is more stable. So this is 1 and this is 2, larger conjugation we can say. First compound RS, if you want to draw, you can draw this way. This comes over here. Double bond, here we have the positive charge, double bond, double bond. Next you can draw, this comes over here. Double bond, positive charge, double bond. Further, you can draw this is the structure we can draw. Clear? Okay. Next one you see. CS2 positive charge, positive charge, positive charge. Order of stability. Are you done? Okay, the first one, the carbocation is resonance stabilized. Okay, resonance stabilized. The second one is what? The second one is aromatic compound it is. Third one is anti-aromatic. Order should be 1, 2, 3. Yes, we have resonance also here, but anti-aromatic compound it is overall. Okay, so this is how we solve this kind of questions, the stability order now. Similarly, we have free radical stability also. We know carbocation and free radical have the same way, right? We can deal with. So free radical stability factor, you see, for free radical, the factors which affects this, the only thing in this aromaticity are not there. So the factor we have here plus M, stabilizing factor, then we have plus H, then we have plus I, D we have minus I, destabilizing factor, okay, then minus H, destabilizing factor, and minus M, destabilizing factor, okay. These three stabilizes, these three destabilizes. So all examples that we have done, there you remove positive charge and add one radical, you will get the same questions for free radical you will get. So for example, you see we have OCS3 here, and here we have CH2 radical. It is exactly same. We won't do much in this. We'll have CH3 and CH2 radical. Tell me the order here. Tell me the order, first one. See, the first one, here we have what effect? What effect we have here? Plus M. Lone pair on oxygen. Plus M. And here we have plus H. Order of stability is this. This is hyperconjugation, 3 degree, then 2 degree, and then 1 degree. Got it? Right? Okay. Next you see carbon ion. The last one we have the first factor we have here, aromaticity, because if the negative charge is a part of aromaticity, it is most stable. Then the second stabilizing factor we have minus M. Third one we have minus H. Third one we have resonance. I have written it separately into this one. We can consider into this also. Then we have minus H, minus I, plus I, plus H, plus M, anti-aromaticity. Okay, this are stabilizing factor and these are destabilizing. Got it? Sorry, it is negative, not plus. Stability order, tell me. For both, it is this. Okay. So what effect we have here? NO2 minus M. Here we have minus I and minus M. So along with minus M, we have minus I also here, and here also minus I. So minus I is more effective at this position. So this is the most stable one, first, second, and this is third. Right? Rank is this. Here we have minus H plus H minus M. Minus M stabilizes more. So it is 1, it is 2, it is 3. Correct? So this is how we compare the stability of carbanion, free radical, and carbocation. Okay. Acidity also we have discussed how to check acidity and basicity. You just need to write down the conjugate base, and depending upon the effect, okay, what effect is there in the conjugate base, resonance, hyperconjugation, or I effect, we can compare the stability of conjugate base, and then what we can say, and then we can say which compound is more acidic or less acidic. Okay. Understood? Few examples of this we'll see. Like suppose you have to compare the acidic behavior, acid base, you write down heading. Okay. The first compound is this. You have to compare the acidic behavior of this hydrogen. H, H, and here we have this. Okay, this is suppose alpha and this is beta. Which one is more acidic, alpha or beta? Tell me, what is the answer? Okay, beta is more than alpha. See, how do we do this? First of all, we'll write down the, yes. So first of all, we'll write down the conjugate base of this. And the conjugate base of the first one is this negative charge. And the conjugate base of the second one is with negative charge here. Now, which one is more stable? Which one is more stable in this? That is a carbanion, negative charge. We can easily compare the stability with that, all those effects. Okay. This compound is what? This compound is aromatic, you see. This compound is anti-aromatic, right? So stability order is this is more stable, and hence the acidity order is this. Is it clear? Easy? Compare the stability here, sorry, acidity here. Benzene with C double bond OOH and benzene with OH. A is greater than B because this COO minus here, negative charge, and this negative charge has more stability. Hence the order is this. Okay. What is the acidity order in this compound? OH on the top. Here we have CH3. OH on the top, CH3. OH on the top, and CH3. Stability order. Done? Done? Okay. You see the negative charge that I am writing down here only. We have O negative here, O negative here, O negative. The conjugate base, correct? Is this. Now this negative charge, you need to check the stability of this. So this one has plus H and plus I. This one has only plus I, and this one has plus H and plus I. So this has the maximum electron density because of plus H and plus I more effective over here. This one is least stable, 3. This is 2. And this is the most stable, we have 1. Hence the acidity order is also this. Okay. Same as the stability order, and which is the middle one is the most acidic compound. Did you get it? Yes. Okay. So this is it, guys. We are done with this chapter. There are other things also, but for KVPY, this much is enough. Okay, if you can understand all these, you can do the questions of KVPY. Okay, so we are done with this session. Okay, next class we'll start with a new chapter. Okay, yeah, thank you. Assignment uploaded on Learnist, you can go through for hyperconjugation and resonance. Thank you.